Thank you. I'm very excited to be here to learn from all of you. I guess just in general, thanks for Swift. We use it a lot, and I'll go ahead and talk about it in this presentation. As mentioned, earlier this year, we released a set of open source projects around containerization, which is a Swift-based framework that allows us to build and run Linux containers on top of macOS. During this talk, I'm really hoping to dig in a bit more into containerization, but really the intention is to highlight how we use Swift to carry out some low-level systems tasks in the process. Give you some guidance on where we'll go on this journey for the last talk of the conference. I'm going to start out talking about what are containers, just kind of a little bit of a level set baseline. I want to dig into some of the design principles we had in making our containerization solution. We'll dive into the actual package itself, or the repo, and talk about some of the modules and everything else that we built. We'll have an example of building with containerization, so kind of digging into a little bit of Swift there. And then I want to tell you the story about our adoption of Swift and what we learned during the process. So without further ado, let's talk about containers. Yep, it's up there. When deploying server-side workloads at scale, these workloads run in many different environments, and containers allow us to isolate the workload from the host as well as from other workloads running. Containers allow us to replicate our deployment environments on our local machine, allowing us to develop and test our applications as if they were running in production. And from an experience perspective, generally for containers, we kind of have this notion and feeling that it's lightweight, it's free, it's an ephemeral environment. So containers do this by allowing developers to package their application and dependencies of that application. Now, these dependencies could be dynamic libraries, binaries, other assets. Having the application and dependencies packaged together allows different containers to have different dependencies from the host or from one another. The result is packaged into a single deployable unit, which is what we call a container. That's gigantic. Containers also provide runtime isolation. A lot of what I was discussing was around kind of more image format. So let's talk about that. Generally, they have an isolated network from the rest of the host machine. And for privacy, processes running in one container shouldn't be able to view or inspect processes running on the host or in other containers. At runtime, containers are able to be sized and scaled independently of one another. So resources like CPU, memory, disk can be allocated based on a per workload basis. I am going to do a demonstration. I pressed Command F1, and it worked. OK, it's way up there. Cool, perfect. So let's say I'm going to show an example using our container tool that's built on top of containerization, all of it in Swift. And I want to run something with an interactive terminal with a set number of CPUs. We'll say 2 CPUs. And it's equal, right? I'm tired. OK. And we'll just run a distro, and we'll run a shell inside of it. OK, great. It started up, sub-second start time. If I take a look at it, I'm no longer in macOS. I'm sitting in a Linux environment. Now let's say that I have some super important but unsecure now calculations to do. And maybe I want to do a few of these. Each of them will saturate a CPU core. If I were to go into another terminal and see if we're doing any of our super important work, I don't see that because it's separate, right? It's running in a separate machine, in a virtual machine, isolated from the rest of the host and isolated from any other containers running. And if I were to take a beautiful look at, you can even read that. It's way up there. You see that despite wanting to run on 6 CPUs, these different threads, I'm only occupying on the host 2 CPUs worth of allocation. So really, I'm just kind of, yes, containers are providing that resource isolation, that view isolation, and they have that feeling of being ephemeral. Let's go back to, oh my gosh, it worked. OK. So now we're all experts on containers at the very most superficial level. But let's talk about the containerization design principles that we had. Well, the design principles we had in mind when creating containerization. Now, in order to run a Linux container on macOS, we need to virtualize the Linux environment. Traditional solutions would be to spawn a large virtual machine to host any of your running containers, and resources are allocated to this large virtual machine. And as containers are added within the guest, the resources are divvied up as needed. When you need to share additional directories or anything with a particular container, what we end up doing is sharing those to the virtual machine before then making them available to the individual container that requested the data. Now, one area that we're focused on is security. And for security, we want to have the same level of isolation that a typical container platforms have with their large virtual machines and apply that to every container that's launched. We also want to reduce the need for core utilities and dynamic libraries built inside of these large virtual machines. This helps reduce the attack surface, but it's also one less thing to maintain. Focus on privacy. So limiting the access of directories or any other resource, it should be done on a per container basis. Only the container requesting that directory should have access to those contents. And finally, performance. We want to be able to hit these goals while still providing a performant experience while respecting the user's resources. So for security, our goal is to provide the same level of isolation of a virtual machine and apply it to every container that is started. Containerization does this by running each container inside of its own lightweight virtual machine, while still providing sub-second start times. This also provides a benefit that each container can be given its own dedicated IP address. So it has performant networking, but also we no longer have to do any port forwarding magic if we want to be able to expose a service from a specific container. When sharing directories and files, we do it just for that single container that requests it. And resources like CPU and memory, if there's no container running, we're not using any CPU or memory. Completely shuts down. Now, throughout the talk so far, I think I've said lightweight virtual machine about 7 times. So I kind of want to talk about that in a little bit more detail. Like, what does that mean? First, we start with like, what is the machine itself? We go ahead and make sure that we kind of are following, well, we're using a minimal number of devices that we need in order to provide this containerization experience. So we use Apple's virtualization framework, and we have just the devices we need, like not a chipset, not a real physical system. We're just looking at, I want a network device, I want a video block, I need a socket to be able to communicate with it, I need a shared file system. This is kind of more of a micro VM model that we're following. And also, we're sizing the virtual machine based on the direct application's requirements. So right-sizing the memory, as well as right-sizing the CPU. So it's a lightweight virtual machine booted just for that. On top of that, though, now let's boot the machine. We need to boot into something, and what we boot into is the Linux kernel. In fact, we do a direct boot into the Linux kernel. We don't have any kind of firmware or bootloader or anything else. This saves on boot time, and as well as it reduces our bill of materials. For this direct booted kernel, we also focus on a minimal kernel configuration. We chose an ARM64 configuration that addresses our needs and minimize otherwise what's included. This is, again, reducing attack surface and ensuring that we have a fast boot experience. And once we're booted through the kernel, we're going to go to user space. So we can talk about a typical initial file system that you would have when booting a Linux virtual machine. Historically, they're booted as a full system. And they have things like libc implementation, dynamic libraries, core utilities like copy, cd, ls, things like this. For security, we didn't want to have to need these things. So we don't have any core utilities. We don't have any dynamic libraries. We don't have a libc implementation inside of it. In fact, we just created our own init process that is purpose-built for running in this constrained environment. And this is vminitd, which is written in Swift, and it's statically built using the Swift Linux Muscle SDK. It's designed to manage the full lifecycle of all the processes that we launch inside of the guest. So running as the initial process comes with different responsibilities before and during container execution in our environment. It's responsible for assigning IP addresses to network interfaces, mounting file systems, such as the container rootfs itself, doing process supervision, being able to launch process, read processes, everything else inside the virtual machine. And it provides a gRPC-based API that we can talk to from the host in order to be able to be directed for spawning and managing processes from the host. So if I step back and talk about my security, privacy, and performance focus, with a minimal kernel, we're getting better security and better boot time. With direct boot, we're getting faster boot time. With static, purpose-built init process, I would say that we're getting better performance for boot as well as security. And each workload being inside its own virtual machine, I think we can say that we get all three. So let's do a quick dive into containerization now and talk more about some of the things we had to build inside of it. First, at the open sourcing, we had two aspects of it. I did the quick demo using container run, etc. That's just a small little client tool that's built on top of, I would say, what the developers and the team are most proud of, which is a containerization framework underneath it. We're going to focus in this section on containerization. So in making containerization, we created many modules while building it out. We have Containerization OS, which provides utilities for interacting with low-level OS components like terminal, as well as doing process management. We created a netlink one so that we could manage those Linux network interfaces. We have an OCI module, so we can work with container images and runtime primitives. OCI is the Open Container Initiative. So just some of those specifications using those. And also we created an ext4 module for being able to, from Mac OS, work with a Linux file system. And I'm going to focus on that one just a bit more and provide a quick example. Each of these are probably worth their own deep dive, but given the time budget, let's just go into this. First, why do I need containerization ext4? Why did we write it? Ultimately, we need a Linux file system for these guests to run in. And for performance reasons, we want to be able to do this on the fly from Mac OS. So traditionally, if you want to be able to create a Linux file system, add contents to the Linux file system, you'd probably running in a Linux environment. We want to do it from Mac OS, and that's what we created. Why? Okay, further motivation on why we did this, in case it wasn't enough, sorry. So the initial file system that I talked about, that vminitd, that's packaged in ext4 block device. So when we're creating our artifacts, we're going to, from Mac OS, take that binary, create a file system, and put it inside of it, and pass that in as block device. And similar, a container rootfs, we're going to add that from Mac OS, work with this thing, create a block device that's ext4, and pass it into the guest also. In creating it, we have a couple of different classes and some key functions that I'll highlight and we'll demonstrate using in a second. First of all, we have a formatter. This allows us to create, format, and manipulate an ext4 file system from Mac OS. The unpack is kind of interesting. We use that one for unpacking container images. It just takes a tarball and puts that whole thing into a file system. And you can do multiple of them into the same file system. Create allows us to do things like create an individual file, directories, symlinks, these types of things. On top of that, we also have a reader. So the reader lets us do the opposite of that tar. We can take out the whole thing and bring it over to Mac OS and inspect the contents, manipulate the contents, as well as get metadata information about it. So I have a brief example. We're going to create an ext4 file system, add content to it, read the file system metadata back, and then export it so that way we can check it out. I won't dive into the code on this one, but no, not that one, this one. Cool. If we go over here, I have a simple project. It's on the containerization repo for working with ext4. And if I were to run it, we're going to go through all those steps. And it's going to pause at each step. So step one is, I'm on Mac OS. Create me a Linux file system, please. And we have that created at this location. So if I go over, we can just remove that container. Don't need that anymore. And do file, we can see, OK, it says it's a Linux file system. That seems interesting. Now, in order to be able to play with it and inspect it, I can actually create a Linux environment, use Linux tools, and check out to make sure that it meets our expectations. If I do, I can use container for that. So in less than a second, I have a Linux environment. We can go ahead and inspect it using dump e2fs. So this is just like an Alpine image. If I do this, it matches what I would expect in that it has the metadata. Like that's how many blocks are. I didn't count, but I assume that this is correct. And we can go from there. Back on the host itself, now we can go ahead and write a bunch of files and directories into it. So this is going to use the unpack command to take a tar, blop it in there, and it's going to create a bunch of files by hand as well. You can look at the code on the repo. So that should be done at this point. And again, I can go to Linux environment to see, did it match what I'd expect? I'm editing it for Mac OS and able to use it and everything else on the Mac side, on Linux side. So in this case, I'm going to run my little helper container, and I'm going to mount it. And then let's just see what's inside of there. So now I'm in the Linux environment. I can play with it. I untarred my vminitd process and everything else, so I can, from here go and see that everything looks about as I would expect. We can leave there, and the next step is we can read out the metadata information for it. So here, because I wrote stuff to it, the number of free blocks are going to be different. So from Mac OS, I can inspect an ext4 file system. It's just a file on the disk. And I see 357. So if we go and do that dump etfs again, dump. OK. We'll see that the number of free blocks is also 357. So it matches what I would expect. And finally, what we can do is we can take the file system that we have. And this could be any ext4 file system we have. In our case, we already know what's in it, so it's not too exciting. But we can go ahead and grab it and inspect it. So if I do tar tf, we can look at it, and it kind of matches the layout of what we inspected when we mounted inside the guest. So my intention on this one, let's see if it goes back. Yeah, is that file systems are complicated, but we were able to do this in 100% Swift. It's a flexible for creating and manipulating these file systems, providing operations for being able to read and write it from Mac OS. And I would say that we have some APIs there that we use for our use case for packing, unpacking, things like this. But I think this is something that shouldn't necessarily have to live in containerization ext4. I would love to hear other people's ideas of how they can use this. It kind of eliminates the need to be able to have a Linux environment to manipulate these files. So let's step back now. We're going to go on to building something with containerization. So I want to go through an example for running an interactive session within Linux and having it from my shell that has working networking. And that's what I have with the CTR example, again in the repo as well. This time we'll jump over to code. Yep, you're done. All right. So here we have another project. And if we're taking a look at this, I'll zoom out just so you can see the whole thing for a moment. And I guess I want to highlight that this is about, it says 58 lines of code, but it's probably about 5 function calls and a lot of comments and boilerplate, so for readability. But our goal, again, is to have an interactive terminal Linux environment for Mac OS as quickly as possible. The first thing I have here is this container manager, which is, well, first I want to highlight that we're importing containerization OS so we can do some terminal manipulation, and then foundation because we're doing some path work. From containerization, we have this container manager, which is pretty cool. It is what does all the heavy lifting that we have for being able to create and orchestrate container workloads. When we create a container manager, we're really providing it 2 key things. One of them is a kernel. We need to boot something inside of the guest. So now we're ready. We have a kernel. And we need a reference to that vminitd process that's going to be an initial file system that we're going to attach to it as well. In addition, we're adding a default network, which is a VMnet network. So on Mac OS, VMnet is key for virtualization networking. So we can go through and have that. Is it fair to bounce back here? Yeah, it seems to be. So after initialization, we have these 3 things. Nothing is happening at this point. We're just sure that we have the kernel locally, we have vminitd locally, so we're ready when we want to start creating containers. The next bit is we're actually going to do a manager create. Well, actually, I lied to you. I'm sorry. First, we're going to grab a terminal. So remember, the goal is I want to have an interactive terminal within my shell on Mac OS. So I need to grab the existing terminal. And again, this is containerization.os, containerization OS. And the main thing I want to highlight here is that we end up having to do quite a bit of syscall to be able to do this low-level manipulation of the terminal. And this is an area where the Swift C interoperability really shines. We have it throughout, but like in the terminal handling, this is definitely a good example of that. So we set it in raw mode so we can grab it later on. When we go to create a container using our container manager, we're providing two things. One of them is we're providing a name. We could have called it potato or London or anything. We called it CTR example here. And then an image reference. So this is whatever you want to run from like a URL perspective. In this case, it's a container, a popular Linux distribution that's small. So we take these and we create the container manager. And what we get back from that is a Linux configuration where I can go ahead and start doing things like setting the resource management. I can go ahead and configure that I do want an interactive terminal. I want to be able to say this is the entry point is just a shell from the root directory. So after we're doing the create, it takes that information, it provides that information back. But the first thing it's going to do is it's going to pull that Alpine image, and then it's going to create an ext4 file system. And then using containerization ext4, it's going to unpack each layer of it so that we have the ext4 file system, and then we're going to have that Linux configuration. So again, nothing's running at this point, but we have all the information ready to go to start a virtual machine. Yes. So, and now after that, what are we going to do? These are the two calls. We're just going to do a create, and we're going to do a start. Create's actually kind of where a lot of the action starts. So this is where we actually now are booting a virtual machine. So we have the Linux kernel in there. We're going to boot through it. We have vminit up. We're going to communicate from our client on the host and tell vminit, here's the container rootfs, mount it, do everything else, and it's ready to go. Nothing's actually starting, but we do have the VM there. It's when we call, OK, let's go into this as well. When we actually create it too, that's where we're going to set up the network configuration. This is where we use that containerization netlink code in order to be able to configure that interface. And we have our gRPC server. So inside the guest, vminit has a gRPC API. It's serving at this point, and it's ready to be told what to do from the container manager on the host. When we actually do start, this is where some more of the fun starts happening. Once everything is up, we can actually direct vminit, and what it's going to do inside of there, this small little Swift init process, is going to do a fork. It's going to set up the process environment. It's going to do an exec of that shell. And then it's going to start monitoring that process, waiting for it to complete at that point. Now, if we were to look at what happens next here, we resize the terminal for our own convenience, so that way everything looks OK. This is just another client call over that gRPC to the guest to say, update the terminal settings. And then we just sit around and wait. This is implemented as a blocking call from the host into the guest, where it's going to do a Swift continuation. And at this point, let's see if in a picture it shows anything better. We're also mapping all the standard I/O of that shell process back to our terminal here. And with the wait, it's just going to spin and wait until it completes. And at completion, what happens is we get a sig child from the kernel. vminit is listening for this, waiting for it. It's going to call wait for. And it's going to see this is the process that died. Here's the exit code. It's going to go to that continuation, return the wait, and then we finally move on, and we're done. So yeah, let's go and just run it. There's kind of a lot, and the intention is to say that that was a lot. I don't expect any to be like, oh, that was fine. But it was also like 4 function calls, and that's it. But we had to do a lot of that low-level stuff in Swift. So if I were to run it, that's it. Like, we're in Linux. We're in Darwin. We're in Linux. We're in Darwin. And like, I think that we had to do these things, but from a user perspective, if you can make 4 Swift calls, you can make them all in one line if you want to. You can do this. You don't have to run a shell. You can do some other kind of utility that's pretty interesting for you and build something more unique. So I think that if I talk to the team, the thing that they're most proud of are some of these APIs and containerization and making sure that they are easy to use. And as far as something to be built on, I think it's powerful, you can extend it, but it's also kind of a proof point that Oh, I can't read my speaker notes. That's why I'm rambling. Sorry about that. There we go. It proves that Swift's kind of ready for some low-level Swift programming. You know, if people are like, oh, I can't do that, it's for this. I think that's wrong. It's good for lowest level systems programming on Mac OS as well as Linux. We're doing it on both sides here. We had to do process management. We had to do terminal management, proxying standard I/O and signal management across a machine boundary. We had to create tooling for manipulating and creating ext4 file systems. We have basic Linux network interface configuration, an IT system with proper process reaping on Linux. We have OCI image management. So we have a lot there, and I think it shows kind of the readiness and the utility of Swift pretty well. So speaking of Swift, I want to pivot a bit then and wrap up and talk about our team's adoption of Swift in writing container as well as containerization. Now, it's kind of awkward to come here and say, like, oh, this is why Swift is so great. Like, I think that y'all probably have pretty good reference points on that as well. It's expressive, it's memory safe, et cetera. So what I ended up doing is talking to everybody on my team about their experience. And for context, my entire team has a good amount of systems experience, 100% in Golang and C. And this project was really our first dive into Swift. So happiest surprises, I would say that interoperability with C was great. The feedback is it couldn't be any easier. As I discussed, we often need this, you know, when going and doing syscalls and everything else. So that's been a great experience with Swift. One of our favorite items, this is from Danny, is that tagged enums and tagged unions or enums really changed how they kind of thought about designing APIs while making containerization. Memory safety has been key based on our focus on security. Many of the team members came from C or Go, so like having optionals help, you know, and they've been really nice to use. What else have we been saying? The static builds, this is just like a basic requirement for the work we were doing in order to have that minimal guest environment. So checking boxes there. We do call a lot of frameworks within Mac OS. So doing Swift to Swift is very native and very nice. So everything's perfect. We're done. Swift is done. So we love it. We came from a different background. So we also had opportunities to learn and opportunities for the ecosystem, I think, to grow. I would say that there are many options, and it's been kind of dynamic how concurrency is for the language from my little view. Our approach for bottom-of-the-stack systems programming across different architectures will certainly take a different approach than a front-end application. And I think that the challenge that we had then was finding out what's idiomatic for our team, what's idiomatic for the kind of architecture that we're running, and that took us time to kind of figure out. But like now knowing that, what I'm hopeful is that it was a learning curve, but with more solutions like this, we know what to do, and hopefully we have more references where other teams know what to do, and we start to answer the question of this is what idiomatic means for such and such. Yep, build that right out. OK. The other one is package ecosystem, which before anyone gets confused on that, I mean that like if we're writing Go and you needed to do netlink, you know that that's the netlink one you go to, and it exists and everything else, and you have that Linux tooling available. And a lot of times we either didn't see or couldn't find some of that functionality that we would need. The great news is we really like writing code, and so it wasn't. It was an opportunity, and I think this is the same thing as some of the concurrency, or maybe even more directly, that as projects make more things, these happen and they exist. And my hope is that some of the stuff that we have in containerization should just live outside of it, and we can extend it and have it ready for other people to use for their use cases. So next steps. If you want, you should try using container as a tool to play with it, to look at it, and inspect and look at the code, anything else. I would recommend taking a look at some of those modules that we do have in containerization. Again, the APIs are suited to our needs, but we're trying to be thoughtful, and I would love to see these grow and live on their own as well in the future. I would take a look at those containerization APIs, build something small with it, see what you can do. It's not like running containers the hard way. it's just a little bit, and container itself is fine, but I bet you there's some more really creative, interesting things we can do using these APIs. And then keep building the Swift ecosystem and keep putting these more out there. So thank you.